Have you ever walked across a carpeted room and felt a zap when you touched a doorknob? That sudden jolt is a common experience, especially in dry weather when the air lacks moisture. The friction between your feet and the carpet generates static electricity, which builds up on your body until it finds a way to discharge. Or pulled a sweater over your head only to have your hair stand on end. This happens because the sweater rubs against your hair, transferring electrons and creating an imbalance of charges. The hair strands, now similarly charged, repel each other, causing them to stand up. These are everyday encounters with static electricity, a phenomenon that demonstrates the fascinating world of electric charges and their interactions. From the simple act of walking to the more complex interactions in our daily lives, static electricity is always present. We experience static electricity all the time. But what exactly is happening at a fundamental level? Atoms, the building blocks of matter, contain protons, neutrons, and electrons. When these electrons move from one object to another, they create an electric charge. These seemingly simple occurrences hint at the presence of invisible forces at play. The forces are the result of the attraction and repulsion between charged particles, which can be observed in various everyday situations. These forces arise from fundamental properties of matter called electric charges. Positive and negative charges attract each other, while like charges repel. This basic principle governs the behavior of electric charges in all materials. By understanding electric charges and their behavior, we unlock a deeper understanding of the universe itself. This knowledge helps us to harness electricity in various technologies, from simple static electricity experiments to complex electronic devices. So, let's embark on a journey into the shockingly simple truth about electric charges and fields, exploring the fundamental laws governing these interactions and their impact on our technological world. From the static shocks we feel to the advanced electronics we use, electric charges play a crucial role. Get ready to be charged with excitement. As we delve deeper into the world of electric charges, you'll discover how these tiny particles shape our everyday experiences and drive technological innovation. Everything around us, from the air we breathe to the devices we use, is made up of tiny particles called atoms. These atoms are the building blocks of matter, the fundamental units that make up all substances. They are so small that millions of them could fit on the head of a pin. These atoms contain even smaller particles called protons, neutrons, and electrons. Each of these subatomic particles plays a crucial role in the behavior and properties of the atom. Protons and electrons possess a fundamental property called electric charge. This charge is what allows atoms to interact with each other, forming the bonds that create molecules and compounds. Protons have a positive charge, while electrons have a negative charge. This difference in charge is what creates the electric forces that hold atoms together. Neutrons, as their name suggests, are neutral, possessing no net charge. They act as the glue that holds the nucleus of an atom together, balancing the repulsive forces between positively charged protons. An object becomes electrically charged when it has an imbalance of these charges. This can happen through various processes, such as friction, conduction, or induction. If an object gains electrons, it becomes negatively charged. This is because electrons carry a negative charge, and adding more of them increases the overall negative charge of the object. Conversely, if it loses electrons, it becomes positively charged. Losing negatively charged electrons leaves the object with a net positive charge. Remember, charge is never created or destroyed, only transferred, a fundamental principle known as the conservation of charge. This principle is crucial in understanding how electric circuits and various electronic devices function. This means the total amount of electric charge in the universe remains constant, a pretty electrifying thought. From the smallest particles to the vast expanse of the cosmos, electric charges play a vital role in shaping the world around us. Just like magnets, electrically charged objects exert forces on each other. Objects with opposite charges, like a positively charged balloon and your negatively charged hair, attract each other. Objects with the same charge, like two balloons rubbed on your hair, repel each other. The strength of this attraction or repulsion is determined by Coulomb's law. This fundamental law, named after physicist Charles-Augustin de Coulomb, states that the force between two-point charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. In simpler terms, the closer two charges are and the larger the charges, the stronger the force between them. This simple yet powerful law governs the interactions between charged particles, from the smallest atoms to the largest lightning bolts. Imagine a group of friends pulling and pushing on a heavy object. The object's overall motion depends on the combined effect of all the individual forces. Similarly, when multiple charges are present, the net force on any one charge is the vector sum of the individual forces exerted by all the other charges. This is known as the superposition principle. This principle allows us to analyze complex charge configurations by breaking them down into simpler pairwise interactions. By considering the individual forces between each pair of charges and adding them up vectorially, we can determine the overall electric force acting on any given charge. This principle is essential for understanding the behavior of charges in more realistic scenarios, paving the way for analyzing complex electrical systems. Section 5. Mapping the invisible electric fields and field lines. Imagine a magnetic field around a bar magnet. You can't see it, but you can visualize it using magnetic field lines. Similarly, an electric field surrounds every charged object. This field is a region of space where an electric charge experiences a force. We can map this invisible field using electric field lines, which are imaginary lines that indicate the direction of the force that a positive test charge would experience at any point in the field. The closer the field lines are to each other, the stronger the electric field. These lines always point away from positive charges and towards negative charges. Electric field lines provide a powerful tool for visualizing and understanding the influence of charges on their surroundings. Section 6. Gauss's Law, Unveiling the Electric Flux Code. Imagine a water balloon with tiny holes. The amount of water flowing out depends on the water pressure inside and the size of the holes. Gauss's law, in electrostatics, provides a similar concept for electric fields. It relates the electric flux through a closed surface to the net charge enclosed within that surface. Think of the surface as a net capturing the electric field lines, which represent the flow of the electric field. Gauss's law states that the total electric flux through the surface is proportional to the net charge inside. This law simplifies calculations of electric fields for symmetrical charge distributions, providing a powerful tool for analyzing complex electrostatic systems. Section 7. Electric double agents, dipoles, and their interactions. An electric dipole consists of two equal and opposite charges separated by a small distance. These dipoles play a crucial role in understanding the behavior of many materials in electric fields. When an electric dipole is placed in a uniform electric field, it experiences a torque that tends to align it with the field. Think of a compass needle aligning itself with Earth's magnetic field. Similarly, the dipole experiences a torque that rotates it until its positive end points towards the negative end of the electric field. This interaction is fundamental to understanding the behavior of polar molecules in electric fields and has significant implications in various areas, including material science and electronics. Section 8. Electrifying innovations from capacitors to touchscreens. The principles of electric charges and fields have led to numerous technological innovations that we rely on every day. From the moment we wake up and check our smartphones, to the time we spend working on our computers, and even when we relax by watching television, these principles are at work. They are the backbone of modern technology, making our lives more convenient and connected. Capacitors, for instance, are devices that store electrical energy. They are fundamental components in many electronic circuits, providing the necessary power to keep devices running smoothly. Without capacitors, many of the gadgets we use daily would not function as efficiently. They consist of two conducting plates separated by an insulator. This simple yet effective design allows capacitors to store and release energy quickly, making them essential in applications ranging from power supplies to signal processing. When connected to a voltage source, opposite charges accumulate on the plates, creating an electric field and storing energy. This stored energy can then be released when needed, providing a quick burst of power to the circuit. Touchscreens, ubiquitous in smartphones and tablets, also rely on the properties of electric fields. These screens have revolutionized the way we interact with technology, making it more intuitive and user-friendly. These screens have a layer of capacitive material that stores electrical charge. This layer is sensitive to the touch of a finger, which is why touchscreens are so responsive and accurate. When you touch the screen, your finger alters the electric field, which is detected by sensors, allowing the device to register your touch. This interaction between the electric field and the sensors is what makes touchscreens so effective and reliable. These are just a few examples of how a deep understanding of electric charges and fields has revolutionized our technological landscape. From capacitors to touchscreens, the applications are vast and varied, continually pushing the boundaries of what is possible in the world of technology. Section 9. The electrifying journey continues. Further explorations in electromagnetism. Our exploration of electric charges and fields has just scratched the surface of a vast and fascinating subject. These fundamental concepts lay the groundwork for understanding more complex phenomena in electromagnetism, including the relationship between electricity and magnetism, electromagnetic waves, and the wonders of electrical circuits. As we delve deeper into this electrifying world, we uncover the fundamental laws governing the behavior of charged particles and their profound impact on our universe. So, stay curious, keep exploring, and never stop questioning the shockingly simple truth behind the forces that shape our world.